So I'm just going to work some of the equilibrium problems so you have these to go back over if you need to. So we're going to start with one that requires a quadratic formula. So it says for the synthesis of hydrogen fluoride from hydrogen and fluorine. So we need to write a synthesis reaction. Hydrogen plus fluorine yields hydrogen fluoride. It's balanced. It tells us 3 moles of hydrogen and 6 moles of fluorine are mixed in a 3-liter flask. So that's our initial. Okay, so our initial concentration of hydrogen is 1 molar, because 3 moles divided by 3 liters. And fluorine is going to be 2 molar. And since it didn't give us a number, we are going to assume that we have 0 hydrogen fluoride. So then we're going to go ahead and do our change. So reactants, subtract, products add, and then our equilibrium, 1 minus x, 2 minus x, and 2x. So then it tells us the equilibrium constant for the reaction, K, is 1.15 times 10 to the second, and it wants us to calculate the equilibrium concentration of each component. Well, to be able to do that, we're going to need to solve for x. So our K expression for this reaction is HF squared over H2 times F2. So if I go ahead and plug in things that I have, and this is all the information I've got, I'm going to plug in 1.15 times 10 to the second equals 2x squared over 1 minus x times 2 minus x. We've got to solve this for x. We've just got one variable in there, so this is doable. It's just going to take some math. So I'm going to go ahead and multiply this bottom up there and FOIL it at the same time. So I'm going to do 1.15 times 10 to the second times 2 minus 1x minus 2x plus x squared, and that's equal to 4x squared. So if I go ahead and distribute, I'm going to get 230 minus 345x plus 115x squared equals 4x squared. Well, to solve this as a quadratic, I need to have this thing set equal to 0, so I need to subtract my 4x squared over and get 230 minus 345x plus 111x squared is equal to 0. Now I can use a quadratic solver to be able to find my value of x. So I'm going to go ahead and enter in my coefficients. 111, negative 345, and 230. So I get two answers. X is 2.139, and X is 0.968. So it can't be both of these answers. It's got to be one of them, and this is where your brain has to kick in a little bit. You have to look back at what each of these x's would cause in your mathematics. And if you pick x as 2.139, and you try to subtract that from 1, you're going to get a negative concentration. That's impossible. So this is not a valid answer. So now I have my 0.968 as my x. That's the one I'm going to use. But my job is to calculate the equilibrium concentrations of each component. That's the goal, which all it means is to fill out that line with numbers. So for hydrogen, I'm just going to take 1 minus my x. I'm going to get 0.032. For fluorine, I'm going to take 2 minus my x. Get 1.032. And for hydrogen fluoride, I'm going to take 2 times my x. And get 1.936. And these are all concentrations, so they're all molar. And that's my answer. So I'm going to work one of the problems with a simplifying assumption. So here we have iodine breaking apart into just 2 iodine atoms. And so it gives us the reaction and asks to calculate iodine concentration and then the iodine atom at equilibrium at 600 Kelvin, it gives us the K. And so I'm going to go ahead and set up my ice diagram. Okay, it tells us that 0.5 moles of iodine was heated in a 2.5 liter vessel. So I'm going to calculate my initial concentration, which is 0.2, and it didn't give me any iodine atom, so I'm going to record that as a 0. My change is minus x and plus 2x, and my equilibrium is 0.2 minus x and 2x. So if I set up my K expression, I get iodine atom squared over iodine. So if I plug in 4, I'm going to get 2.94 times 10 to the negative 10th equals 2x squared over 0.2 minus x. And this would end up being a quadratic, which is not any fun. But what you can do is you can look at your K value, and if it's pretty small, that means the reaction is not going to go very far to the right. That means x is going to be a pretty small number. And so what we can do is say that 0.2 minus x is approximately equal to 0.2, that we may be subtracting 0.0001 or something like that. As a general rule, to make sure that this assumption is okay, you can take your initial concentration, so here would be 0.2, and if you divide it by the K, if the number you get is greater than 400, then the assumption is probably valid. That's just a rough estimate. Okay? And when you actually do this one, this thing comes out as 680272108, considerably larger than 400. So we're going to go ahead and say that this is a valid assumption. Well, that cleans up the math a lot for us, because now our equation becomes 2.94 times 10 to the negative 10th equals 4x squared over 0.2. And it's going to get rid of our need to do the quadratic formula. So if you go ahead and solve this, you get 4x squared is equal to 5.88 times 10 to the negative 11th. X is going to equal that number divided by 4, and then square rooted. So x is 3.83 times 10 to the negative 6. And if you did look at your x value, and you subtracted 0.2 minus 3.83 times 10 to the negative 6, you do approximately get 0.2. It doesn't change a whole lot. So the goal is to calculate the I2 concentration and the I concentration at equilibrium. And so we're going to go ahead and do that. And so I'm going to bother to calculate this. And I get that the I2 concentration is equal to 1.9999 times 10 to the negative first, which is essentially 0.2. And then the I concentration is going to be 2 times x, which is 7.66 times 10 to the negative 6. And those are both molarity. So the simplifying assumption will save you some quadratic formulas. On the other hand, if you look at the same question and we raise the temperature, our K is significantly larger than it was before. So if you were given that same 0.2 molar to start with, if you check the assumption, do 0.2 divided by 0.209, this is clearly going to be less than 400. This comes out as 0.957. This is not a valid assumption. So on this question, you would end up having to do the quadratic formula. You would not be allowed to just simply say 0.2 minus x is approximately equal to 0.2. So most of the problems that we've looked at have one side initially being 0. And that's a pretty easy problem, because we know which direction that the reaction goes right away, because you can't subtract from the 0, so you must be adding to the 0. So the 0 side has to be a product. But if the initial stage has numbers for everything, it has a mixture of products and reactants, you have to figure out which direction the reaction goes by comparing Q and K. Okay, so we've done this several times, but we haven't done it with the calculations. So we're given a reaction here. Okay, and it gives us in one experiment 1 mole of methane, 1 mole of CS2, 2 moles of H2S, and 2 moles of hydrogen are mixed in a 250 milliliter vessel, and it gives us the temperature, or the K for that temperature. So if we wrote out our ice diagram, and gave our initial amounts, we have to do them in molarity, so we're going to have to change these. So we should get 4 molar of that, H2S, 8 molar, CS2 should be 4 molar, and H2 should be 8 molar. And so that's initial, and so as you can see here, this is different, because now, how do we know which direction to put the minuses and to put the pluses? And so we're going to have to know K, and we're going to have to check Q against K. We're going to have to see where we are right now. So our Q reaction, or equation, is CS2 and H2 to the 4th over H2S squared and CH4. And so the Q expression, you don't have to be at equilibrium. You can plug anything in at all. And so our Q is going to be 4 times 8 to the 4th over 8 squared and 4. And so our 4's are going to cancel out. You can do this in your calculator, but a 4 is going to cancel out. We're left with 8 to the 4th over 8 squared, which is 8 squared, which is 64. And so when we set up and we compare our Q and our K, and so our K is 0.036, which is much less than our Q. So the reaction is going to go to the left. So the question here said, in which direction will the reaction proceed? Reaction shifts left. Okay, so that's going to tell us that the stuff on the left is our product and the stuff on the right is our reactant, because it's going that direction. So what we're going to have to do is finish out our ice diagram, okay, because then it gives us in part B that the methane concentration is 5.56 at equilibrium. What are the equilibrium concentrations of the other ones? So I'll quickly just copy that ice over. So 4, 8, 4, and 8. So for our change, since we see the reaction going to the left, we're going to add x and add 2x, subtract x and subtract 4x. And then our equilibrium line is going to be 4 plus x, 8 plus 2x, 4 minus x, and 8 minus 4x. Well, this should make, given the data, this should make a little bit of sense to you, because it says the methane concentration is 5.56. Well, the methane concentration started at 4, and the only way that it's going to reach 5.56 is if it went up. So we're going to have to add to that, even if we didn't know the answer to question A, we could have figured it out from the information they gave us. So they did give us that K was 0.036 up above in the example. So we're just going to set up the expression, same as Q. So we're going to put our CS2, which is 4 minus x, okay, over times 8 minus 4x to the 4th, over 4 plus x and 8 plus 2x squared. And this would be a beast of a problem. However, they saved us a little bit by telling us that methane was 5.56. Well, we can go into our ice diagram and say that 4 plus x has to equal 5.56. That means x has to equal 1.56. And now I can quickly put those all in. And the question isn't even to solve for any k. We were given that. It's just to find the equilibrium concentrations of the other substances. So we just have to know x. So H2S is going to be 8 plus 2x. So that'll come out as 11.12. CS2 is going to be 4 minus 1.56, which is 2.44. And H2 is going to be 8 minus 4 times 1.56, which is 1.76 molar. So we're going to continue doing the Q versus K to check. So the giant hint for this is if your initial line doesn't have a 0 somewhere, you have to check Q. Okay, so it says we're studying a reaction of the phosphorus halides, and we mix 0.150 moles of PCl5 and 0.05 moles Cl2 and 0.05 moles of PCl3 in a half a liter flask. Okay, it gives us a K and asks which direction the reaction proceeds. So we need to be able to set up our Q, and so I'll just write quickly our ice diagram so you can see why we're doing this. So our initial line, we have to divide each of these by a half liter. So PCl5 is going to be 0.210. PCl3 is going to be 0.09. And that's the same for Cl2. So we don't have a 0 anywhere, so we don't know which direction the reaction goes. So our Q expression is going to be Cl2 times PCl3 over PCl5. And we're going to go ahead and plug in. We have all those concentrations. So Q is going to be 0.09 times 0.09 over 0.21. If we go ahead and calculate this, Q is equal to 0.039. Well, K is equal to 0.042. So if we compare Q and K, K is greater than Q, so the reaction is going to proceed right. Alright, so then the next question tells us if the PCl5 concentration is 0.2065 at equilibrium, what are the equilibrium concentrations of the other components? So again, given this information, we could have gotten our way to figuring out that the reaction proceeds right without solving for what we just did, but they won't always give you that information. So if you notice, the PCl5 concentration did drop from what it was, but we knew that the reaction was going right anyway. So there's our completed ice diagram. And so they told us that 0.21 minus x has to equal 0.2065. And that's an easy way for us to calculate our x. Okay, so x is 0.0035. Well, I can go back in and figure out the concentration of PCl3, which is going to be equal to the concentration of Cl2 because those are the same numbers. So I'm going to take 0.09 times, or I'm sorry, plus 0.0035. We get 0.0935 molar. Okay. And once again, we're looking at reaction direction. So this one has a little less direction than we were given in the previous one. It just says carbon monoxide reacts with steam to produce carbon dioxide and hydrogen. Well, we should probably write a reaction for that. So carbon monoxide reacts with steam, which is or gaseous water. So that is important because it goes in our equilibrium expression to produce carbon dioxide and hydrogen. We're going to have to make sure that it's balanced, which it is. It says that at 700 the equilibrium constant K is 5.10. And it wants us to calculate the equilibrium concentrations of all species if 1 mole of each component is mixed in a 1 liter flask. Well, if we start off initially, we're going to mix, these are each going to be 1 molar. Okay, because 1 mole per 1 liter. So as you can see, we don't know which direction the reaction proceeds because there's nobody that's at a 0. So we're going to check our Q. So our Q expression is CO2 times H2 over CO and H2O. So we plug all those in. Hopefully it won't take you very long to figure out that those are all 1s. So Q is 1. So if we compare K to Q, K is bigger than Q, so the reaction is going to go to the right. This is 5.10, this is 1. So the reaction is going to shift right, which means that when we get to our change line, we're going to go minus x plus x plus x. It's very important to be able to tell which direction you're going, otherwise everything's going to be messed up. We have all our equilibrium concentrations. It didn't give us any other information other than what K is, so we're going to have to use the K expression. So I know that 5.10 is going to equal my products, 1 plus X is 1 plus X, over my reactants, 1 minus X and 1 minus X. And most of you will go ahead and write this as 1 plus X squared over 1 minus X squared. And so now we've got this, fun little equation to solve. So this K is not really small. The assumption is not going to work here. So we're going to have to do some messy algebra here. So we're going to take 5.10 and I'm going to multiply it by the 1 minus X quantity squared, but I'm going to FOIL that at the same time. And FOIL the other side. And I'm going to distribute. And to be able to solve this, we've got to put all our variables on one side. So I'm going to go ahead and move everything left, just because it'll keep my X squared positive. It doesn't really matter. So I'm going to get a 4.10X squared and a negative 12.2X and a positive 4.10. And that's going to equal 0. So then I'm going to go into my quadratic solver. And I'm going to type in 4.10, negative 12.2, and 4.10. Go ahead and hit solve, and I get two answers. And hopefully you can see that the answer that's the 2.589 is not going to be right, because I can't subtract that from the 1 and get a positive answer. So that's not going to be valid. I can't have a negative concentration. So my X value is going to be 0.386. But that's not the answer to the question. The question was, what are the equilibrium concentrations? Which means, hey, find these numbers that are in the E line. So both my CO and my H2O are going to have the same concentration because they're both 1 minus X. So we'll take 1 minus 0.386, which is 0.614, and my CO2 and my hydrogen are both going to be 1 plus 0.386, which is 1.386 molar. Okay? So those are my equilibrium concentrations. Finally, we're going to do one more of these. Assume that the gaseous hydrogen iodide is synthesized from hydrogen gas and iodine vapor. So we want to go ahead and write an equation about the synthesis. So hydrogen gas and iodine vapor yields HI, and we have to put a 2 there. So the equilibrium constant is 1 times 10 to the second, which we call 100. It's just got 3 sig figs. And says, suppose that hydrogen iodine had 5 times 10 to the negative first ATM, and H2 at 1 times 10 to the negative 2 ATM, and iodine at 5 times 10 to the negative 3 ATM are mixed in a 5-liter flask. Calculate the equilibrium pressures of all species. Okay, so we're in pressures. So we're going to go ahead and deal with that. Okay, so our initials are going to be H2 is 0.01 ATM, and I2 is 0.005 ATM, and HI is 0.5 ATM. And so we're going to have to check which direction this reaction goes. So we're going to have to check our Q, which is the pressure of HI squared over the pressure of H2, the pressure of I2. So my Q is 0.5 squared over 0.01 and 0.005. This comes out to be 5,000. So if I compare my Q and my K is much larger than my K, so the reaction goes to the left. Okay, Okay, so if I go up into my change line, I'm going to be going to the left, so I'm going to be minusing 2x, and then adding x. And then my equilibrium line is 0.01 plus x, 0.005 plus x, 0.5 minus 2x. Okay, so then I can plug these all into k, the k expression. So I have 0.5 minus 2x squared over 0.01 plus x and 0.005 plus x. And that's equal to 100. And so something important to note from this is that even though the reaction is shifting to the left, the equilibrium constant that we are given is given for the direction that was written, okay, as the products over on the right. Okay, even though it's going the other direction, the K number that they gave us is for the reaction as written. So if you want to do it the other way and always do what you think are the products, you're going to have to adjust the K. And so that means you're going to have to flip the reaction around, and that new K would be 1 over 100. I think it's just a little bit easier just to leave it. So this is not a fun math problem from here. We're going to have to distribute FOIL and then distribute the 100. So I'm going to get I'm going to go ahead and FOIL out the 0.5 minus 2x. So 0.25 minus 2x plus 4x squared has got to equal 100 times 5 times 10 to the negative fifth plus 0.015x plus x squared. So we keep doing the algebra. Okay, and then I'm going to move all my values to the same side, so I'm going to move them to the right, and so I'm going to have 96x squared plus 3.5x minus 0.245 equal to 0. Go back into my quadratic solver. And enter in 96, 3.5, negative 0.245. Go and hit solve. And so if I'm looking at my values, first of all, I have an x value as a negative, and I already said the reaction is not going to do that, otherwise that would mean the reaction was shifting to the right. I have a second x value that says x is 0.035. That's going to be my value. X is 0.035. And the question is to calculate the equilibrium pressures of all species. So I'm going to go back through and figure out all their pressures. So the pressure of H2 is going to be 0.01 plus X, which comes out to be 0.045 atm. The pressure of I2 is going to be 0.005 plus 0.035. And the pressure of HI is going to be 0.5 minus 2 times 0.035, which is 0.43 atm. So those are your equilibrium concentrations.